All right, so we are still talking about C13 NMR. Huh?
It is, oh,
C13, yeah. Well, last time all we did is kind of a short introduction. We talked about a little bit about what is similar between C13 and proton NMR and what's different. And we talked about the fact that C13 NMR is much less sensitive for two main reasons. One, that there's a very low natural abundance of C13. Of course, you could get around that if you synthesize compounds and put in a C13 label, right? So that would get past that, and people do that kind of thing. And because the magnetogyric ratio is roughly 1/4 of that of protons, so it ends up being that the energy gap is lower, and so the frequency is lower. And we know that if the energy gap is lower, then because of that Boltzmann distribution, there's less net magnetization at a lower field. And then we started talking a little bit about decoupling. We just kind of showed what it was. And we looked at this slide here, and the main reason that we use decoupling, well, I guess there's two reasons. One is to just basically simplify the spectrum a little bit more because as we'll talk about, the coupling constants are the one bond coupling constants are quite large, and so you get a lot of overlap of peaks, even though there's the part per million spread is pretty big as well. But so we get, better resolved peaks, and because with C13 being insensitive, taking a multiplet, a quartet, or a triplet or something, and putting it all into a singlet means the peak is going to be much higher, and you can get by with less signal to noise. Okay, because just on this one, notice on the coupled spectrum here, the baseline is a lot more noisy. Right?
Why is it so noisy, the baseline here?
Okay, so remember the way we run these experiments is that we pulse and acquire data, and we do that over and over again if we have to. And the advantage to that is that as we add more and more experiments, as we add the data together, the actual signals will all be positive, and they'll just keep adding up. Mm-hmm. And the noise, because it's random, will cancel out. Okay? But because C13 is insensitive, then lots of times we don't... Well, we might not get very many until we run a lot of scans, or we run a certain number of scans until we can see the peaks just fine, but there's no reason to keep running it until the baseline looks smooth and flat.
Mm-hmm. Here it is smooth, or it's not smooth here, the first one?
The first one is pretty smooth, but you can still see some noise in there, right? It doesn't really look like a proton NMR spectrum that would be much smoother than that. But, the signal to noise is it's pretty good in both of those. We don't really have any problem picking out the peaks out of the baseline. But if we had, a small quantity of sample, like I used to do doing natural products chemistry, you'd isolate some small amount of material, and, you may have to run your C13 overnight or longer, to get enough signal to noise to be able to pick the peaks out.
Can we say for each carbon atom we have one peak here, or
in the decoupled spectrum, right? So this one down here, this one is the decoupled. So all the peaks are singlets. we still have the same constraints as far as seeing every carbon, that there could be symmetry in the molecule, right? So some peaks could be the same, essentially. Or we could have some that were just coincidentally overlapped as well.
What is coincidentally meant?
Oh, they just happen to be the same, for various other reasons. Huh?
Is it kind of experimental error, or?
No, it's not error. It just means that whatever the structural influences are, they just happen to be overlapped.
Oh.
Yeah. And we've seen that in proton NMR. And, like in proton NMR, one way you could perhaps get around overlap like that is by switching solvents or something like that, or going to a higher field, or, something like that.
Oh, okay, to have higher resolution.
Yeah.
Distinguish them.
Right. All right. So let's talk a little bit about decoupling, okay, about the process. So there's a lot of ways to actually, fancier ways to do decoupling. They have a lot of different kind of pulse sequences and things to do this very cleanly, but we'll just talk about the basic way. So the way that we might think about this is if we just draw out down here the pulse sequence for the C13. So one difference in, of course, in comparing this to proton is we're just going to do this at a different frequency, whatever the frequency of the carbons is. So like if we have a 400 megahertz NMR, we call it 400 megahertz, which would mean that the protons are resonating at roughly 400 megahertz frequency. The carbons, remember, because the magnetogyric ratio is 1/4 of that, the carbons would be resonating at roughly 100 megahertz, right? So we are going to have a C13 channel at that frequency, and then we'll see we have one at a proton frequency as well. So here we're going to start out just like we did before, relaxation delay. Then we're going to have our pulse. So I'll call this P1 for our main pulse, and that could be various tip angles and times. And then we have our acquisition. This is the acquisition. And then we do that again. We have the relaxation delay, P1, and our acquisition. And we just repeat this as many times as we need to, or as long as we have NMR time. Acquisition. Okay, so for decoupling, remember when we did the selective decoupling in the proton NMR, the main thing here is that we have the decoupler on when we're doing acquisition. Okay, that's what removes the decoupling. So in this case, we're going to do what's called broadband decoupling rather than selective decoupling, in that we're going to be irradiating the full range of the protons. And essentially the way we could draw this out is we'll draw it like this. We'd essentially turn the decoupler on the entire time. Okay, so it would just be fully decoupling. And so this has a couple of effects. One is that it decouples the interaction between the protons and the carbons. Okay, so it removes the splitting for the carbon-hydrogen bonds. The second thing that happens, though, is that because we have the decoupler on during the relaxation delay, we are creating nuclear Overhauser effect. Okay? And in C13 NMR, what that usually is, so we're putting energy into the protons, and it's going to transfer its energy to the adjacent carbon, so the carbon that's closest in proximity. Okay, so we are going to generate NOE, and this goes from the protons, because that's what we're decoupling, to the C13. And one effect that this is because this is a enhancement, the NOE causes an increase in the size of the signal of the nucleus that's receiving the signal. It's going to increase the size of the peaks that have protons attached. Okay, so it increases size of protonated carbons. And in general, because of that, it would increase the size of a methyl group more than a CH2, more than a CH, and the quaternary carbons aren't going to receive any nuclear Overhauser effect. Okay?
Because they have more protons.
Because they have no protons attached to them, or none close enough, right, to give them.
And how far this energy can go to the NOE? Is it just one carbon adjacent to
No, because remember in proton NOE, they could be, I think it's like maybe 4 angstroms or 6 angstroms or something like that. But the amount of enhancement decreases in like 1 over the distance to the 6th power. So it drops off very fast as you go farther apart. Yeah. So this is one of the reasons, remember, that we talked about that we can't integrate the size of the peaks in the C13 NMR spectrum, because they have differential amounts of NOE. So that's one reason. All right. So there's different other ways to do this decoupling as well. Okay, so this is one reason for unequal peak heights, I guess, cannot integrate. Oops. Integrate. Okay.
Peak heights cannot.
The areas really would be more correct, but usually C13 peaks are pretty sharp, so the height is probably pretty representative of the area as well. Okay, so the other main reason for this differential peak heights, we have, so I guess we're going to talk first about other reasons why, here, let me go back and write that here, has to do with the relaxation. Okay, so the T1 relaxation is highly variable in C13 for the carbon atoms. Okay, so T1, especially for quaternary carbons, is much longer than for the protonated carbons.
Is it just because of the NOE?
No. So the T1 is different than the NOE. And so remember that in order to get correct integrations, we had to make sure that we allowed the nuclei to fully relax between our
Different
pulses. But in C13, because the quaternary carbons have a much longer T1, sometimes we don't, usually we don't wait long enough. And so they don't fully relax. And so that also gives us different size peaks. So here I could just say, so usually this relaxation delay is not long enough for full relaxation. And in general, for example, the T1 for something like a methyl group would be on the order of seconds, whereas a quaternary carbon could be, up to minutes.
I was going to ask, just like extend, why don't, I was going to ask why we don't extend it.
Right, but if you had to wait 5 times the T1 in between to get full relaxation. So we usually don't do this in our normal, just a normal run-of-the-mill C13 spectrum, okay? And what we sacrifice is being able to integrate the size of the peaks. Okay, and the nuclear Overhauser effect we essentially already said. And so we see signal enhancement. That comes from signal being transferred from proton to C13. And theoretically, this enhancement could be on the order of 0 up to actually 3 times.
I didn't understand this part, the Nichols-Hauser effect on the C13.
Mm-hmm.
So can you just explain it one more time? Yeah.
Well, essentially we irradiate the protons, and as the protons relax, that energy has to go somewhere.
To other adjacent carbons.
Yeah, and so it goes to the closest atoms is the next carbon over.
Oh, and it enhances the signal.
Yeah, so it enhances that signal.
Oh.
And so the more protons there are, the more enhancement there would be. And so that carbon can end up being up to 3 times bigger than it would be without any NOE.
But can we see all of the carbons that have more protons adjacent to them has more signals or higher
Well, I
signals?
think it's
Or it depends on.
well, so there's more to it than just that, right? Because there's also the size of the signal also depends on this T1 relaxation, right? So the different carbons are going to have different relaxations. If they all relax completely, I think then the carbons that have more protons would be bigger than the carbons that have less protons. But it's not as probably straightforward as that. So we can run the experiments in different ways to either benefit from NOE and things like that, or to run it so there is no NOE. So we could get away from that effect if we want to. Okay, so the first one that we'll talk about is called an inverse gated decoupling. Okay, and in this case, so in each of these cases, the C13 channel is essentially just what we did before. We have our relaxation delay, we have our pulse, and then we have acquisition. Relaxation delay, pulse, and then acquisition like this. Okay, so we just continue on this way. proton channel is where the difference comes in. So in the inverse gated decoupling, what we do is we have the decoupler off during the relaxation delay, and we turn it on during acquisition. Okay, so off during relaxation delay, on during acquisition. Okay, so what do we think? How would this influence what we see in the spectrum?
Will you just acquisition from the C13s?
Yeah, the C13 is where the acquisition is, right? So we're not ever actually acquiring signal from the proton. Yeah. So, two things. One, what about decoupling? Will this spectrum have proton decoupling?
It should.
Yes, because we have the decoupler on during acquisition. Okay, so that's when we see decoupling. So we will see a decoupled spectrum. What about NOE?
We will not have it.
That's what I'm thinking. It'll be, well, if we either don't have it or it's drastically reduced.
Right, so in general, we would have no NOE, because usually we generate the NOE by having the decoupler on or irradiating those protons during the relaxation delay. Okay, so essentially we have no NOE.
It's completely no, or just a reduced effect of NOE?
I think it's essentially no. Yeah. And so, if we run this experiment with the relaxation delay long enough, say it's greater than 5 times the T1, because we removed the NOE, we should be able to integrate the carbons in this spectrum with inverse gated decoupling. But it's not usually practical for us because, for one, we have no NOE, so we're not gaining from this signal enhancement, and the relaxation delay is going to be so long that it's going to be really slow and cumbersome for just running down to run a C13 spectrum. But if you specifically needed this information, you could run that experiment, right? You could integrate the carbons.
But in that scenario, you will have lower signal-to-noise ratio.
Yes, absolutely. Absolutely. So either if you had enough sample that signal-to-noise wasn't a big problem, right? Or if you just ran it for a long time.
To get the peaks.
Yeah. Question?
No, I'm trying to think of a situation in which I would actually need
Right.
the integrations.
Right. Right.
I
I mean, yeah, you may not. It's more like if you didn't know anything about the molecule and stuff like that, right?
that makes sense. Yeah.
And then you didn't have other ways to
If this is the
tell.
only thing.
Okay, so if there's an inverse gated, there's also a gated decoupling. Okay, and this is just kind of the opposite of that one up there. So we have the C13 channel, which is the same. Like this. And the proton channel is just the opposite. So it's going to turn on during the pre-acquisition delay and then turn off during acquisition. So on, off, on, like this. Okay, so what's the effect going to be here? What's our spectrum going to look like?
NOE, but coupling.
Right. So it would be coupled.
So is it decoupling, gated decoupling, or gated coupling? Because it's coupled.
I think it's still called gated decoupling, but good question. Because if there's no decoupling, I guess the idea would be that you're turning on the decoupler. So that they probably, when they first did this, they called this extra radio frequency that was in the proton range the decoupler. So they're gating the decoupler, this proton, this transmitter that's in that range.
The higher signal to noise ratio probably in the second one because of having the NOE.
Right. So it's going to be coupled, and we will have NOE, so we should get better signal to noise, at least for the protonated carbons. Right?
And we cannot integrate it here.
We cannot integrate it. Right. So, if you wanted to actually have a coupled carbon spectrum, this would probably be the way to do it. So if you needed to, for example, measure proton C13 coupling constants or something like that, then this might be a way to do that. All right, so let's look at some examples where this goes into play. So this is this diethyl phthalate. So this is like a common plasticizer. And you can get these compounds from rubber tubing and other places that can get in your samples. And in fact, it's kind of embarrassing to say, but when I was in grad school, so I was trying to isolate these compounds from insects, and we'd wash, with a solvent the insects, and usually you just have little vials, and the way you would remove the solvent would be to blow a stream of nitrogen over it. Because it wasn't easy to hook it up to the rotovap or something like that. But, you can add contaminants that way as well if your tubing is not clean or anything else. So I isolated this compound, UV active, everything, and I was all excited, and I went down. I spent all night on the NMR running these selective decoupling experiments and everything because I had a small amount. And then I took it into my boss to show him. I was all proud. I had been working so hard, and he's like, oh, yeah, that's some phthalates like this, So I'll never, the C13 isn't so characteristic, but the proton NMR has a pretty characteristic spectrum, so.
So it was a kind of contamination you're saying?
Yeah. So it was a learning experience, and so from then on, whenever I saw that in a sample, I immediately knew what it was. All right, so here's a couple of examples. They're all of the same compound, but just with different experimental parameters. So the bottom one is kind of a normal C13, decoupled C13 NMR spectrum with just broadband decoupling. And the relaxation delay is less than what the T1 value is. Okay? And so what we see here is that the quaternary carbons here and here, so we have one for the ester. So this would be the ester, right? And this one that just says 0.17, I guess those are intensities or something like that. would be the two quaternary carbons here, because of course this molecule has symmetry down the middle, like this, right? So notice, even though the carbons are all 1 to 1 to 1 to 1, right, because there's symmetry down the middle, look at how much smaller those two quaternary carbons are. And you really can't tell the CH2s and the CH3 and even the protonated CHs are all pretty big. But the quaternary carbons are very small. All right? If we use the inverse gated spectrum, make sure I got this right, inverse gated, yeah, with the relaxation delay less than the T1, it's a little better, right? So because the protonated carbons have no NOE, then when we set the intensity, to, I guess in all of them, this methyl group is being set at 1, then we notice the quaternary carbons are bigger than they were with the normal broadband. But if we do the inverse gated decoupling and we have a relaxation delay greater than 5 times the T1,
For a long time.
yeah, now we notice that essentially all the peaks,
Have the same high.
yeah, and so you could integrate, well, they did, you could integrate those and get the correct
How
ratio.
practical is that one, the last one, inverse gated?
Well, it just depends on, if you don't need that information, then it's not really worth it. I guess they don't say for the number of, for the same amount of sample, how many scans they had to do or anything like that. I'm not sure exactly that. But in general, or they didn't really tell me in this book where I got it. I think this is from our text. Exactly, the difference in number of scans that they did or anything like that. But it can make a big difference. But on the other hand, when we look at C13 spectra, oftentimes, because it's not run like that top spectrum, we can pick out quaternary carbons because they're the small ones. So we can use that information to our advantage as well.
Oh, always the quaternary carbons are
Well, usually.
usually.
Yeah. If you think back, have you run C13 spectra?
No, well, I'm teaching.
Oh,
spectroscopy
right.
right now.
Yeah.
And so I'm looking back at the spectrum, or the multiple spectra, and I think I see that. I think I'll have to double check it.
It's usually always, especially carbonyls are almost always small. And if you look at things like this, like benzene rings and stuff like that, usually the quaternary carbons will be smaller. Though sometimes they're smaller, partly because, say, there's some symmetry, and maybe the protonated carbons are 2s as well. But usually the quaternary carbons are small. Yeah.
So I have a question.
Okay.
So it's a good kind of sanity check if you're writing out a structure, but I guess my thing is you shouldn't rely on that.
No, I don't think you should, use that as some absolute,
Okay.
but it's consistent.
Yeah. Okay.
Right. Yeah. And we'll learn, we can use other experiments to confirm that. Yeah.
Oh, yeah.
Okay. So let's look a little bit more at coupling, C13 coupling. So we're going to look at some C13 coupling constants. Okay, so in general, when we look at one bond carbon-hydrogen coupling, we can kind of generalize, if it's just some kind of alkyl group or something, that the size of the coupling constant is proportional or is related to the hybridization of the carbons. Okay, and it works out that if we take the percentage of S character in that carbon and we multiply it by 500, then that puts us in the right range of the carbon-hydrogen coupling constants. So for example, if we have an sp3 hybridized carbon, then our one bond carbon hydrogen coupling would be 500 times 0.25, and so it comes out to be about 125 hertz. And it's not exact, but if we look down at this table right here, this is for methane. Well, and even for, ethane, one bond coupling constant for methane is 125. For ethane, it's 124.9, so it's pretty close. But then so this coupling, if it's depending upon the S character, is also going to depend upon bond angles, because as we change bond angles, we actually change the hybridization of certain bonds, right? And we've seen this a little bit before. So as this, that's not right. As this bond angle gets smaller, then we have more, as it goes from, normal sp3 is 109.5, right? But as we make that bond angle smaller, going towards 90 degrees, then essentially what we're adding is more P character, okay? And as the bond angle gets wider, we're adding more S character, okay? So if we look at these, so here's cyclohexane to cyclopentane to cyclobutane. If we go from here, we're changing just the size of these bond angles. This way we have more P character. And when we're in the carbons, so this is a carbon-carbon bond, is more P character. But as we make the carbon-carbon bond smaller, the hydrogen-carbon-hydrogen angle gets bigger. And so that means it's getting bigger, so there's more S character, right? So there's more over here, we have more S in the carbon-hydrogen bonds. And as we increase the amount of S, the coupling constant gets bigger. I think that was the same even with the proton, with like the geminal couplings when we looked at the ring sizes. As the hydrogen-carbon-hydrogen bonds got bigger, then that coupling got more positive. And here it's getting bigger. So we notice, some of these with three-membered rings and stuff, those are, quite a bit bigger than this calculation up there. All right, if we do sp2, then our one bond carbon-hydrogen coupling would be 500 times 0.33, and so this comes out to be about 166 hertz. And so here's some examples over here. Here's sp2, this was sp3. So some of these are smaller, 148, 160, 170. So those are kind of in that range. And SP would be 500 times 0.5 would be 250. Right, so here's some examples, alkynes down here. 249. Okay, so the size of that coupling changes as we add more S character, it gets bigger, both from straight hybridization and from bond angles, which also changes hybridization. Okay? All right, so what are some applications? Why do we care? All right, so for one, if you were working on carbohydrates, and I had this because we used to, of course, have more people in here from Dr. Chang's group as well. But for example, the one bond coupling depends if we have some cyclic acetal like this, which would be like a sugar. You know, if we have OHs on the rest of the carbons, if this H is axial, then the coupling constant is between 158 and 162 hertz. Or if we would call this a beta anomer, or if it's equatorial, or this would be the alpha anomer, it's between 100, it's bigger, 169 to 171.
Do you know the angles of these ones, or?
Yeah, I guess. Well, it must have to do, for how some of these kind of things, it depends upon how this other oxygen is adding electron density. So there's some change in electron density and bond length and things like this. But so if you had a sugar ring like this and you were trying to determine whether it was an alpha or beta anomer, and you could measure that one bond coupling constant, then that would give you a lot of information about that. Okay? And so there's two ways that we could determine that. Determine this one bond, oops, I can't fit it in there, CH. So what are ways that you can think about?
So we're looking for
The one bond coupling constant for one of these bonds here.
How, like, experiments we find it?
Yeah.
Just do the inverse gated.
Right, we could just
wait,
run,
Wait, yeah, it wouldn't be inverse.
it'd be the gated decoupling, I think.
Yeah, the other one.
Yeah, so we could just run just a coupled C13, however we did it, right? And we got, for those carbons, we'd get a doublet, and we could measure the distance. All right? But there was another way that we talked about earlier that might work for this as well. Where we could actually determine it not from the C13 experiment, from the proton NMR experiment. Okay, so let's say, and maybe it wouldn't be this simple, but let's say in the proton NMR, we've got a big peak like this. Right. Okay, so this would be the protons that are attached to, I can't write to the edge there. These would be the protons that are attached to the C12s. Okay? But the protons that are actually attached to C13 atoms would be split. And so we would get some small peaks down like this. And this part would be the proton attached to C13. And right, so the intensity of these small peaks, well, if you put them together, I guess, into a singlet, it would be 1.1%. So I guess it would be half of that or something because it's split into a doublet, right? So these are the C13 satellites. And so then we would just measure this distance right here. Right? And so we might be able to do that. Again, they're going to be quite small. So for one, you have to have enough sample that you can blow that up and have a clean enough spectrum. And it needs to be such that these C13 satellites are resolved from other peaks.
So what information does the distance between two satellites gives us about the coupling of the C13?
Yes, so that's the one bond carbon-hydrogen coupling constant. And in this case, if we measured this and it was 170 hertz, then that would tell us that we must have the alpha NMR of this sugar rather than the beta, right? The beta would be more like 160. So that would be one way to tell, so that gives us quite a bit of information just from that one experiment. The other ways, of course, would be have to do with proton-proton coupling, right? So if these are protons here, in this case, over here, this proton would also have a large coupling constant to the adjacent axial. So you have a diaxial coupling constant. Remember, at 180 degrees would be bigger. This one over here would have only smaller couplings because it only has gauche interactions, right? So 2 hertz or 3 hertz or something like that. Right, so ideally, the more ways you can, add to your data that supports a structure, then that's good. All right, so another example, when I was a postdoc, there were people in our group that had isolated this compound down and left from a marine tunicate, a sea squirt. And the question when they were doing this, had to do with this methyl group right here. And they weren't sure whether that methyl group was attached to a sulfur like this, so a thiomethyl, or if it was just directly attached to the benzene ring. And so the data that they used was they looked up, data like this and found that if it was just a methyl group, then that one bond coupling is usually about 126 hertz. Methoxy groups are more like 146.
Close to the sulfur.
Yeah. Well, yeah, but you could tell the difference, I think, that it wasn't methoxy because the chemical shifts are quite different as well. But the chemical shifts of the thiomethyl and just the methyl are pretty close. And so they were able to tell because of 141, it was bigger like this rather than 126 or something like that. And I actually I used that NMR database just to see how close those chemical shifts were. So I used these compounds so I could put some other substituents on here. OCH3 and CH3. And this said that this one would be at about 11.9 chemical shift. And if I did the same one with a thiomethyl, then this was at 15.5. So not exactly the same, but pretty close. And so then it was the actual coupling constant that gave them, more data to support the presence of this thiomethyl group.
I didn't understand the second one, as you said. So, what type of information we got from the second one that you draw the structure right now?
So what they did, I think that they actually used the C13 satellites, if I remember right, on the proton NMR. So they measured, and I can't remember if this was the one they measured or if this is the kind of standard or baseline for that. But they measured this one bond coupling constant, and that was much more consistent with the thiomethyl rather than the methyl directly attached to the benzene ring. So this rather than this. So you have, information about coupling, chemical shift and coupling constant. And these kind of compounds are kind of tricky to work on because they just have a lot of quaternary carbons, right? There's no proton NMR coupling as you go around some of these substituents around the aromatic ring. So it can be challenging. Okay, so two-bond coupling. So these are going to be much smaller. So we won't really see these in those big splittings. But two-bond couplings kind of are similar to the geminal couplings. So they're like the geminal couplings. So these are okay. So like those, as the angle between them increases, the two-bond CH coupling becomes more positive. Because remember, some of the geminal couplings were technically negative. And as the bond angle became wider and there was more S character, they became more positive, but they actually went closer to zero, so the absolute value got smaller. So other places where this might play a role, if you do two-bond couplings, so some of these, again, are like sugars or acyclic compounds that have, some of them have alcohols. We'll look at a paper much later at the end of the course that does acyclic stereochemistry based upon, various proton and proton C13 coupling constants. But so one example here is if we have a OH on a carbon here, and we're looking at a coupling between that carbon and a proton on an adjacent carbon, so a two-bond coupling. If the H is 180 degrees away from the OH or ether, then this coupling was greater than zero, and if it was 60 degrees or gauche, it was somewhat less than zero. Though down at the bottom, it didn't quite fit there. So one example here, again, is like for a sugar. we looked at the one bond couplings from this hydrogen here, but the two bond couplings also vary. So if here's the one where this proton, it's like this example here, this proton is 180 degrees away from this OH, then this two bond coupling is greater than 0, so it's 1 hertz. Whereas if the angle between this and this OH is only 60 degrees, then it's less than 0, is minus 5.7. So this is another way to tell, I guess, the stereochemistry of alpha or beta anomers on these sugars. For acyclic ones, it was a little bit different. From this other paper that I used that we'll look at later, if we have this same situation, if the proton is anti to the alcohol, then this said it was in the 0 to minus 2 range, so it's still more positive than when these are 60 degrees angle. Then it was minus 5 to minus 7. The bottom ones is if it was a 1,2 dioxygenated. So that would be, so if there was another, I think, alcohol or ether on the back carbon on the one where that proton is on. And so those were a little bit different. Okay, so this other paper we'll look at, they use all these coupling constants to be able to determine relative stereochemistry of acyclic molecules. Is pretty tricky. All right, so if we do 3 bond couplings, so this is like the vicinal coupling constants in protons, where we have 2 protons like this, and it depends upon the dihedral angle. So remember, this follows what we call the what was called the Karplus relationship. And remember, we had this graph that was like this, and this was, this was coupling constant, and this was a dihedral angle. This is the angle. And at 0, it was like this, and then it went down, and then it came back up like this. So this was at 90, and this was 180. Right, so the coupling constants were larger when those atoms were in the same plane. So there's better orbital overlap. Bigger when they're anti, still bigger but less when they're at 0 degrees. So this is kind of the range here for this 3-bond proton-carbon coupling, around 9 hertz when they're anti. Closer to 0 when they're 90. And around 6 hertz when they're eclipsed. Okay, so and of course, like gauche, like 60 degrees would be small, in between 0 and 6. Down here on the bottom, these are the examples. These are for 1 oxygen, and this is for 2 times oxygens on these 2 carbons. And so if they were here, if they were anti, 6 to 8, so just a little bit smaller than we said up there. And if they're gauche, 1 to 3, so a little smaller. Well, no, that's about what we would say for 60 degrees. Some other vicinal ones, so like when we looked at proton couplings on double bonds, if groups were trans, it was a large coupling constant. If they're cis, it's smaller. So this is the same thing. If these are cis, this is about 7.6 hertz. Oh, I have it over here. So cis, And if they're trans, more like 12.6. So for the proton carbon coupling. I think this is only 2 bonds, but this was about 8 hertz. And then the other place that we could see some of this is on a benzene ring. So here's coupling to that carbon that's in red. So if it's a 1 bond coupling, then it's quite large. And if it's a 2 bond coupling, so this is like the ortho position, 1 to 4, 3 bond is actually bigger. And then the 4 bond is small again. And this can have some impact on how you can set up 2-dimensional NMR experiments. If you're looking at proton-carbon coupling and whether you want to optimize them for 3-bond coupling or 2 or 4 or something like that. Okay? All right, so enough of coupling constants. All right, so let's talk a little bit about chemical shifts now. Okay, so what we said before is that it generally kind of follows the chemical shifts of proton NMR. You know, in that sp2 is further downfield. Here it says sp3 minus 20 up to 100 parts per million. 100 parts per million would probably have a couple of, like something like this, like an acetal or something like this, with 2 oxygens might be at 100, right? But it's still sp3, sp2 between 120 and 240, and sp again is kind of in the middle, 70 to 110, right? Electronegativity impacts the chemical shifts, just like we've seen before, causes de-shielding. If we put electronegative groups, minus 2.3 for methane itself, we shift downfield if we have, say, a nitrogen that's more electronegative than one of those hydrogens, oxygen down to 49, fluorine down to 75. So the more electronegative that group, it just pulls electron density away from that carbon and causes de-shielding. Okay? Of course, if we have 2 of those groups, then it's kind of additive, various things like that. All right, so here's a few examples, too, that can influence it. So resonance, electronegative groups, resonance can influence it. So let's say that this first X is an electron withdrawing group. And so I'm going to actually put the most common of these would have some kind of a...
Fluoride.
Huh?
Fluoride or iodine.
Right, those would be electronegative, but iodine, those aren't going to be so involved in resonance, though. Mm-hmm. So electron withdrawing groups that have some kind of resonance will usually have some pi bond here with an electronegative atom here. Okay? And the type of resonance that they'll have is that the electrons will be drawn out of the ring up onto this electronegative group. So we get resonance structures that look like this. I'll just do it like this with a minus up here. Oops. Come on. This would put a plus here, right? And we can always just keep moving these around the ring. Minus down here. Of course, we can do it one more time. Minus over here. Okay, so No, what am I doing? Pluses there, not minuses. Pluses. So we should see more deshielding at the ortho and para positions. Okay, so this benzonitrile, the second one over on the right, is kind of an example, right? Because these electrons can be drawn up onto this nitrogen, so this can be pulled out this way. So we should see a delta plus at the ortho and para positions. And as an example here, I think I have all of these written down.
It's disconnected the HDMI cable or tablet.
Oh.
Maybe.
There we go. Thanks. Yeah, I guess I hit it with my arm. Okay, yeah, here. Let's see, I don't have that one. So nitriles themselves are at about 119. So this one's 119.2. This one would be is at 132. 129.2. 132.8. So there's not a huge difference, but the two that are ortho and para here are slightly further downfield. Okay. And so other groups that can have electron withdrawing like this, any of the carbonyls or nitro, any of those will have the same kind of resonance. Okay. So electron donating groups are usually groups that have non-bonding electrons, so they push electron density into the ring. So we have a resonance that goes like this. And a minus over here. And then we can just continue on around the ring like we did with the other one, but we're pushing the electrons are in the ring this way. So we'd have a minus here, and so what we end up with is we have a partial negative.
And more shielding.
More shielding then, exactly. Okay, so up here is an example. So this aniline, the nitrogen, can donate electrons into the ring. So we should have delta minus, delta minus, delta minus, right? And these chemical shifts vary, like this is 116.1, 129.8, and 119.0. Right, so notice that the ortho and para are much more upfield than the meta. Right, and then for this case, if we have a nitrogen directly attached, so now we just have a carbon that has an electron withdrawing group on it, so that's more like the previous slide. This is at 147.7. Okay, so the direct attachment of the nitrogen causes deshielding. Okay?
Yeah.
Carbonyls, right, have resonance like this. Right, so that's going to cause deshielding, and then probably there's this, anisotropy, diamagnetic anisotropy as well, and so carbonyls tend to be the most downfield. And so, for example, acetone is at about 206.7. All right, and in general, here's another carbonyl down here. If we have non-bonding electrons here, we can do the same kind of resonance that we did up above. But then these non-bonding electrons can donate electrons and reduce the amount of delta plus, remove the amount of de-shielding on that carbonyl carbon.
With electron donating groups, I think, at the same time.
Right. Well, they're going to be atoms that have non-bonding
non-bonding
electrons on them. Yeah, that can donate. So like oxygen or nitrogen, things like that. So the way that this kind of shakes out, if we have ketones or aldehydes, then the chemical shifts are usually greater than 190. Okay? And if we have groups that have oxygens or nitrogens, things like esters, carboxylic acids, amides, things like this are usually in the 165 to 180. All right, so we can tell the difference between, ketones and aldehydes and the rest based upon that. Okay, what else? Okay, we can do 1 minute here. Conjugation also affects chemical shifts. So when we have an isolated double bond, these are like 140.2 and 112.8.
We're back here.
Okay, yeah, we're almost done.
Oh.
Yeah, it's time anyway.
Okay.
We could just stop right now. Pick up this next time. What else? Because we are almost... let's just stop there. Because we got a couple more things on chemical shift. And then we'll start looking at spectra. Oh yeah, you guys got homework for me too, huh?
I do.